Okay, so we covered rolling. All right, now I want to look at the kinetic energy of a rolling body. All right, now remember, we saw that rolling was a linear combination of pure translation of the center of mass plus pure rotation about the center of mass. Okay, so here I have a rolling wheel, okay, rolling to the right. And what I did is I just took a snapshot at one instant, okay? So on the wheel, I drew the direction of the velocity v, okay, of points on the rim at different times, or at different places. So at that point, that part of the rim is headed in that direction, okay, in that direction. This point of the rim is headed in that direction, and so on, okay? So what we're gonna do is we're trying to find the kinetic energy of something that rolls. So all we know so far is the kinetic energy due to rotation. Remember, the kinetic energy due to rotation is 1/2 I omega squared. Okay, so now I have a rolling wheel that's rolling, and this is going to be rolling by at constant omega. So the center mass is moving by at constant speed. So this wheel is rolling by with angular speed omega. Okay, has a moment inertia I, but it's also translating to the right. So that's how we're trying to find the kinetic energy of a rolling object. Okay, and we're going to treat rolling for now as pure rotation about an axis that passes through the stationary point of contact. So what that means is as this wheel goes rolling by, okay, and I'll show you a video right now of a wheel rolling by. All right, so if I look at this point of contact, so the wheel goes by, I take a snapshot, and I want to say, we're going to treat the wheel as if this big wheel is rotating about that point. Now what I mean by that is I'm going to scroll down, okay? So this wheel here, okay, that one right there, the one in black, okay, that's the original wheel in the above picture, okay? And you can see the velocities I drew here, okay, are the exact same for that picture, okay? So what I did is I said, okay, at this instant, when that wheel is in this orientation, okay, there's the center of mass of the wheel right there, okay? At this instant as the wheel passes by, it looks like the wheel is purely rotating about this axis, okay? And what I mean by that is, so the black wheel, okay, is in position number 1, okay? And if the tip of the wheel was nailed, okay, so there's a pivot point, whoops, okay, so it's nailed right there, okay, so there's a pivot point. Okay, so when the wheel's at position number 1, it looks like there's a pivot point right there where my axis is, okay? Now, if I wait a little while, now the wheel's in position 2, okay, and it's moving, okay, in that direction. Now the wheel is in position 3, all right, still pivoted about where our axis is nailed to the ground, okay? I wait a little while longer. Now the wheel is at position 4. A little while longer, the wheel is at position 5, okay? And then right when it gets back up to the top, I'll call that position number 6, okay? It's back up to the original black colored wheel, right? So I look at that and I say, oh, well, position number 1 and position number 6 just look like different positions when the wheel is just rotating around, okay, with the rim nailed down at that contact point A. Okay, so when this wheel comes rolling by, okay, and I look at this picture right here, at this instant, you can't tell whether the wheel was rolling by, okay, to the right, okay, or if I had a big hoop, like a hula hoop, and it was pivoted about point A, and it was just going around in a circle. Click. So right when it's at position 1, which is the same as position 6, it's doing the exact same as it would if it was moving to the right, okay? So the velocity of the center is to the right, the velocity of the top, okay, we know is twice that of the center of mass, all right? And then what I did is for these different positions, for position number 2, okay, that would be the center of the mass of position number 2, and it's headed in that direction. Here's the center of mass of the wheel when it's in position 3. Okay, here's the center of mass of the wheel when it's in position 4, okay, and position 5, okay, and so on. So this rolling wheel, okay, as it rolls past, right at that contact point, okay, it looks like a snapshot of a wheel that had the center of mass rotating. So I'm going to use a different color. Okay, I'll use yellow. Might be hard to see. Okay, so look what the center of mass of the wheel is doing. Not a perfect circle. Just like that. So that's this right there. So a rolling wheel, okay, we can treat as pure rotation about an axis at the contact point. Okay, so again, as that hoop, okay, gets moved around and then comes back up to the top, right when it comes back up to the top, different points of the wheel are doing the exact same thing as when the wheel was rolling. Okay, so to analyze rolling, we're first going to treat this wheel as pure rotation about the contact point. Okay, so to find the kinetic energy, because we know the kinetic energy of rotation, that's 1/2 I omega squared. So here's our axis A, about which the wheel appears to be rotating about. Okay, so it's 1/2 moment inertia about that axis times omega squared. All right, and again, it's the same omega, because if I look at V center of mass is R omega. Okay, and that was the center of mass, I think, of position 5. That was the center of mass of position 2. Okay, this is the V center of mass of position number 1, and they all have the same omegas. Okay, as it moves around. Okay, because for position 1, omega 1 was the same as omega when it was rolling. Okay, so it's the same omega. Now, how do I find the moment inertia about axis A? Parallaxis theorem. Okay, so the moment inertia of that wheel, okay, about axis A is I center of mass plus mh squared. Okay, remember h is the perpendicular distance between those two axes. So if here's my wheel, there's the ground. Okay, that's my new axis. That's the center of mass axis, and the distance between those two axes is the radius r. So here h is r. So that's what I put right there. Okay. Okay, so I just multiplied this out. Okay, brought the omega squared in. Okay. Now, in this chapter, we're often combining r omega, because r omega is the speed of the center of mass. So r omega squared is v center of mass squared. So now I can call this the total kinetic energy, okay, because we alluded to before when we did rolling, that when a wheel rolls, it's a linear combination of pure rotation about the center of mass plus pure translation of the center of mass. So now for a rolling object, the kinetic energy is two parts. You have the rotational kinetic energy about the center of mass and the translational kinetic energy of the center of mass. So that subscript is important, okay? You can't leave that subscript off, okay? You can't just write it as V, because we know different parts of the wheel have different V's, okay? So that's why that subscript is really important, always has to be there. And the first time we started using that subscript was in the tube lab, okay? When you rolled the ball came out, and we had measured different heights, H2, okay, and so on, H1, were measured from the floor to the center of mass. So now we write the kinetic energy. Okay, total kinetic energy is the rotational kinetic energy plus the translational kinetic energy. Okay, now, if you remember from that lab, okay, there was a term in that lab where we had to include a rotational kinetic energy. Okay, and I said that we have to wait and see where that comes from. Right? If you take a ball, roll it on the ground, you have to sit through 11 chapters of Physics 195. Okay, so there's that much math wrapped up into the nature of rolling a ball. Okay, so we had a solid ball, okay, and the total kinetic energy is the rotational kinetic energy about the center of mass plus the translational kinetic energy of the center of mass. Now we know for a solid sphere, this is one of the ones we have to know. Okay, so I is 2/5 mr squared. So where the I is, okay, so that's the other good thing about this chapter is this is the only time you get to talk about what I is, right? In English class, you can't say I is. Okay, so I is 2/5 mr squared, put that right there, okay? And that's my translational kinetic energy, all right? But, and again, this is how we compare these two in this chapter. R omega is V center of mass. So here I have R omega. I put in V center of mass squared. Okay, so R omega is V center of mass squared. Okay, and then that's where the 2's go away. I have a 1/5. Okay, and now I add these together. Okay, remember from algebra class, you have your 1/5 plus 1/2. So in this chapter, you're often adding a fifth plus a half, right? So the common denominator would be 10. So multiply top and bottom by 2, top and bottom by 5, and you have 7 plus 5. No, you got 2 plus 5, okay, which is 7, divided by 10. Okay, so a fifth plus a half is there's the 7/10. So when we did that lab, that's where the 1/5 came from. Okay, it came from canceling out the 2's, and that's where the 7/10 came from. Okay, and again, the 2/5, that comes from a big messy integral that I had posted before. Okay, so there's a ton of math wrapped up in nature. Okay, now for rolling hoop, okay, so if you take like a roll of tape or a rim, okay, or a ring. Okay, so again, a hoop is this wall is thin. Okay, so the total kinetic energy for a rolling hoop, take a ring and just roll it. Okay, there's the rotational kinetic energy about the center of mass, translational kinetic energy of the center of mass. That's why you need to know those shapes we talked about previously. So moment inertia about the center of mass, okay, for a hoop, right? We know what I is, right? Remember, that's where all the mass is as far away as you can get. So that's why that coefficient is 1. So that coefficient's a 1, right? There's a 1 there. So I put in what I is, all right, mr squared. And then again, we're doing this so often in this chapter because we want to compare that term with that term. And the way to do that is you say, okay, R omega is V center of mass. So R squared omega squared is V center of mass squared. Okay, and I have a half plus a half, okay, and that gives me a 1. Okay, so for a rolling hoop or a rolling ring, the total kinetic energy is mv center of mass squared.